Hey guys, how are you doing?
Hi.
See if our other two come soon. Let's just hang out for a sec. Let's see. Mackenzie and Emmy are usually a team, so let's give them a couple of minutes. Anything you want to talk about while we wait? Any questions or anything? Homework questions? Silence. Abby, you don't have a way of communicating with either Mackenzie or Emmy?
I don't.
You don't. Okay. Okay, let me see. Well, hopefully they come. Well, let's go ahead and start some. I mean, let's see. I don't think I've looked at the DQ post since yesterday. Jessica, I did respond to your DQ post. So I don't know if you want to talk about that some, or Abby, do you have a question like on some homework you're working on or anything?
Think I just kind of made corrections to the homework based on your feedback. So I think I understood it. I don't know if I really have like a question on it. It's funny because actually there was like another typo that I found, or at least I wanted to ask about whether or not it was, but now I can't remember what problem it was. So that's what I was looking for. But I mean, it was like a small thing. You kind of like knew what it was anyway. But
So there was so there were two things with you. One was the homework questions for your project, right? So that was one of the things. And the other thing was this problem from the last homework set, right? So what you turned in didn't seem to really address a lot of what's there, but that's also a really good problem to work through. I mean, because it's sort of a typical of what we're doing in this section.
yeah, I was like I just posted it because I was like, oh well, this is all I'm finding right now of like what to do with it. But then with like the questions that you asked, I was able to kind of figure out what like everything was looking for to like prove each part. And
Did
then
you repost it already? I can look at it just to
I
get.
didn't repost it. I just changed it to the homework, but I could take another screenshot and repost it of like
Oh
what
yeah, yeah, yeah. Repost. I mean, that's the point of the discussion is to actually discuss, right? Not just because I
so
won't. I mean, I probably won't actually look at your homework, right? But if you post a repost in the discussion, I'll probably actually look at it,
right.
right?
Yeah, okay. Yeah, I can do that. I don't know if you saw my email response, but like I originally had it as like the order of G being 6. And so then that way like the 2 and the 3 would make sense, and then the answer really would be that like the the subtraction would mean that it wasn't empty. uh
Mm-hmm.
but then I was like, oh, well, if it's 5, then I could check to see if they knew that the identity element wouldn't get counted twice.
Mm-hmm.
And I
Mm-hmm.
forgot about the fact that they had to multiply. So it was like best laid plans, you know?
I mean,
But
that's what I yeah. So that's what I mean when I said I thought I could see what you were doing.
yeah.
Let me just see here. What is this? Sir. Not seeing that. Okay. But I was actually talking about your DQ, because you were the only person, I think, or maybe two of you had posted DQs for this week. When I looked yesterday, I don't think I actually got a chance to look today. Let me just go poke around in there real quick, because that's actually what I was talking about, because that's like on today's topic, and the one you did was good. It's just what you did wasn't enough for what I wanted to see there.
Yeah, both. But you had like asked about both at the beginning, so I just responded. But yeah, no, I fixed both of them, I think.
Oh, here we go. I think we got some other people coming in. Yeah. Okay, good. Okay, Abby's coming. Good. Glad to see you. Let me see. This is like topic 60Q1. Oh no, it wasn't that. Must have been DQ2. Let me see. Yeah, okay, I see. You just said thank you, that helps. So that was yeah, so I mean, that's a good one to look at. So maybe I'll talk a little bit about the stuff that I had left over to do. I see everybody's cat people, or not. Well, I don't know about Jessica, but Abby's a cat person. Mackenzie's obviously a cat person with her background. I've got two cats that sometimes might jump on my desk here at any moment. Let me talk some, just finish up this one set of lecture. I mean, I did put a video here, so I'm not sure if people have had a chance to look at it yet. And then if no one has any other questions, we can look at this particular problem, because it's a good, this one, and there's another one sort of related to this one that are really sort of good samples of like what we're doing in chapter 19. So that those are good things to look at. And of course, I mean, you not getting it quite right is good, because it gives me something to talk about.
I was also looking at number 36. Maybe that's the other one, because that was the one I was going to ask about. It's very similar to 25.
I think it's similar. If I'm not mistaken, 36 works out quite differently than 25, which is what makes the pair kind of interesting, right? Well, let me say a little bit. Actually, I don't really remember what we got through last time, so let me share my screen. I know I hadn't made this last video yet, but I think maybe I did talk about some of this stuff. Okay, get that there. By the way, Mackenzie, do you know, is Emmy coming, or is he?
Yes. Yeah, he texted me 5 minutes ago that he's going to be 5 minutes late. So
Okay.
he'll come.
Okay. Good. Okay, so so I think we introduced this notion of reducibility last time. So what does it mean to say in an integral domain that an element is irreducible? Anyone? What does it mean when you tell a kid that an integer is irreducible or reducible?
It's like if it's
Any-
prime. Yeah.
Say it again.
Like, can't be factored any further, basically. Like, it's
Okay, if it factors any further, meaning that I mean, you can't always factor, like in R, right? You can always factor anything, right? Like if I take alpha, right, I can always write it as other things, like alpha minus 1 times alpha, right? Or I can write it as beta minus 1 times beta times alpha, or something silly, right? Because I have units all over the place, right? So factoring only makes sense up to unit multiples, right? As soon as you have a unit, you can just throw in extra units all the time, right? That's like saying you can add 0 as many times as you want, right? You can multiply by 1 any way you want to. You can add 0 any way you want to, right? When you're doing algebra, right? So something was irreducible if whenever you have a equals b times c. So you think you've factored it, right? One of these is actually a unit, right? And the other one is then, so if one of these is a unit, then it means the other one isn't equal to a, but the other one is, say, an associate of a, right? So that just means they differ by a unit multiple, right? So that's what that means. Good. So that's what irreducible means, that if something, I mean, another way of saying this is kind of like what we do with when we define primes, right? If something divides A, then either that thing is an associate of A or it's a unit, right? Like when we say P is prime in the integers, either, you know, P divides the thing. That's the only two things that divides P, right? If P is prime, is 1 and P, right? But of course, -1 also divides P. So we could say in the integers, the only thing that divides P is a unit or P, right? Or so, I mean, really, literally, right? Like what are the things that divide 7? So it's really plus or minus 1, so a unit, right? Or plus or minus 7, right? So something which is an associate of 7, right? Okay, so we tend to forget the plus or minus parts when we teach it to kids, right? But it really is here too, right? What does it mean then officially to be prime? So when is A in an integral domain prime?
If it's not a unit,
No, I mean there's lots of non-units. Can you think of a non-unit in Z which isn't prime? Like 6 or 4 or any right, or any non-zero number that's or any number besides plus or minus 1, right? That's not prime, right? So there's lots of those, right?
You have on the screen the P is prime if and only if the only divisors of P are 1 or negative
Okay.
1, P or negative P. And
Well,
then
that's in Z, right? So that's what prime means in Z. I mean, that's our definition of irreducible, right?
uh,
So this is really, I mean, this is what's being said here is when we teach kids what primes are, we teach them two kind of things that are equivalent in Z, but are not generally equivalent, right? So one of them is the first one, which is really saying P is irreducible, and one of them is the second one, right? Which is how we define prime, right? You guys need to internalize this. This you should understand, right? What is a prime ideal? Let's just go back to the beginning, right? What does it mean to say K is a prime ideal? It means if I can multiply two ideals together and they get inside of K, right? Then one or the other is inside of K. Right? That's what it meant for ideals to be prime, right? And what was another way of saying that this ideal was prime was to say if AB is in K, then say Emmy's coming, right? Either A is an element of K or B is an element of K, right? So that's what it means to be a prime ideal, right? Everyone shake your head anyway. Sorry. I'm gonna make you all stand in a corner if you can't answer questions or something. All right, okay. So what is a prime number? What is a prime in an integral domain? Here, Emmy, you just came in, so you have to answer this. what does it mean for A in an integral domain R, right, to be prime? How do I know that A is prime?
One more time the question.
So I have an integral domain R, I have A in an integral domain R. I claim A is prime. What does that mean? What does it mean to say A is prime?
are you only asking him?
Well, the
You-
G,
Oh.
it has to be a unit.
See, everyone's saying the same thing. What does it mean for, so you missed the first part. What does it mean that for A to be irreducible? It matters, right? The whole point of this is that it matters, right? These are different notions and generally, right? So what does it mean to say A is irreducible?
Is that where either, so is that where if you have A equal to, there's something about if you have A equal A times B equals 0, then either A is 0 or B is 0? Does it have to do something with that?
Okay, what is that called?
Ah, let
Jessica,
me
what
look
is
at my
that called?
notes.
If I have two non-zero things that multiply together to give me 0, what is that called?
Let me look at my notes.
Or Abby, what is that called? I have two non-zero things that multiply together to give me 0. What is that called?
Zero divided.
Zero
Well,
divisor, right?
Okay.
If a times b equals 0, right, and neither a or b is 0, then that's a zero divisor. We're in an integral domain. Are there any zero divisors in an integral domain? What is the definition of, gosh, what's the definition of an integral domain?
They never have zero divisors.
They don't have zero divisors, right? Okay, so we're working in an integral domain. So being prime or irreducible have nothing to do with zero divisors because there are not any. If you guys don't start answering questions better, I'm going to have part of your test like live in person, right? Because you're supposed to be knowing some of this stuff, right? So look up here at the notes, the thing you can see, right? In Z, when we're teaching kids about what prime is, right? We usually use these two things that we say is equivalent, right? So P is prime if the only divisors of P are plus or minus 1 or plus or minus P, right? Okay, we tend to forget the minus ones, but they're there. That's one way of saying something's prime in Z, right? The other way is saying that if P divides A times B, then P divides A or P divides B, right? One of these is irreducible and one of these is prime, right? So we just discussed irreducibility, right? Saying that something is irreducible means that if A equals C times D, now this might sort of hint at what you were thinking, but it's not 0. If A equals C times D, right, then either either C is a unit or D is a unit. Right. So the only way we can factor A is for one of these two things to be a unit, right? That's equivalent to saying, so this is exactly equivalent to saying either C is an associate of A, because that just means that it's a unit times A, right? Or D is an associate of A, right? So in Z, right, we're in Z. How does this play out, right? So in equals m times s, right? Two integers, right? Okay. We're saying n is irreducible if and only if m or s is plus or minus 1, right? Or equivalently, m is an associate of n, so it means you just multiply m. So what does that mean? It means m equals plus or minus n. Those are the only associates in Z, right? Because the only units are plus or minus 1, right? Okay. Or, right, or m is an associate of s, right? So this is irreducible, right? So this first thing here is irreducible, not prime, right? Okay. So after all of that, when A is in an integral domain, what does it mean to say A is prime? Anyone?
If A is not a unit and it can divide like a multiple of two things.
Look, the two things are right here, right? There's two different statements right here. You see where I'm pointing? The first one is irreducible. It's something about units, right? The second one doesn't say anything about units, right? What does it say?
That it's divisible by AB.
No, what does it say? Try again. That's not what it says.
P is divisible by the
No,
product of AB.
sorry. This is not a symmetric relation, right? This is not saying P is divisible by AB. What is it saying?
Oh,
What
that P is a
what did P-
divisor of AB.
So if P divides A times B, then what?
Then it either divides A or B, but not both of them.
Both, it doesn't matter. It either divides A or B, right? It can divide both. I mean, it could be that P divides P squared, right? Then P divides both of them, right? P times P. But if P divides a product, then P is divide one of the things in the product, right? Okay. Okay. What does it mean for A to be prime? Mackenzie.
Something with the 0 element, like it cannot be 0.
Emmy, help out Mackenzie. That's what Emmy said when you first walked in.
I know.
There's nothing about zeros here. There's no zeros anywhere in this, right?
What
When we
about
said- when we-
Is
Go ahead, Jessica.
A is irreducible.
Oh, you're
like-
reducible.
Well, no, I'm asking what prime is. Tell me when A is
Yeah.
prime.
If prime, then that means that A is irreducible.
No, that's not. There's a definition. There's a difference between a definition and a theorem, right? There are two different notions here, right? One is prime, one is irreducible, right? Two different things. So the question is, what does it mean to say A is prime?
If it can divide like a factor of a number, of like a multiplication of two numbers, if it can divide one of the factors.
Sitting right here in front
Oh.
of you, right? It's right there, right? What does it, I mean, Emmy just read it, right? You guys have this situation in your own classes where you're like, what does the number one mean? Can you give me an instance of
just-
one?
We're
Can
just
you-
Yeah, it's like the end of the
we're
year.
just defining prime, right? So
What does it mean to say, yeah, so right here is a definition of P is prime in Z, right? Right up here is a definition. We use both these definitions for prime, but I've already told you this first one is really saying P is irreducible in Z, right? So the second one must be saying P is prime in Z, right? So now forget Z, right? Go back to an arbitrary integral domain. How do I define P is prime, right? So forget A, P. P is in R. How do I define P as prime?
then when you have a product like BC, it divides B, it's a divisor of B or a divisor of C. That's
So I want you to say the correct, so you sort of said half the correct thing. Say the correct thing. It's an if-then statement, right? There's a hypothesis implying something. You got to say
Yeah.
both parts correctly,
if
right?
P is the divisor of the product A and B, then P is the divisor of A or the divisor of B.
So,
Yes.
okay, closer. There's not a the divisor. If P divides,
Yeah.
right? It's a verb, right? If
Okay.
P divides A times B, then P divides A or P divides B.
Okay.
Right. So I have a hard time believing that you've done the studying for this
Mhm.
week, since if you don't know this, it's hard to do a lot of the other stuff that was in the text, right? 'Cause this is like a key concept in the text here, right? I will ask you again to see if you forgot. We need like flashcards where I come back every 10 minutes and ask to see if you remember what we just talked about, right? So real carefully, let's just get this, right? So we're in an integral domain, right? No zero divisors, so we don't talk about zeros. Division has nothing to do with zero, right? It's like it has something to do with one. It has nothing to do with zero, right? So P is prime. If and only if this is the definition, this is the only definition of prime, right? If P divides AB, then, right, P divides A or P divides, B, right? So the definition, okay, go away thing. This is by definition, right? It's not a proof if and only if, it's like a definition if and only if, right? The definition of P is prime, right, is this thing down here, right? So I mean, literally, I'm doing 509 too, so sometimes I write this stuff out carefully. This is like for all A and B, right? You know, in R, if you like, right? In the division, in the integral domain, right? P divides AB implies, you know, P divides A or P divides B, right? This is a sentence, right? Sort of phi of P. It's a sentence about P, right? So P is prime means exactly phi of P holds, right? Like that. So I mean, the statement needs to say, when this happens, then that happens, right? To say something's prime, right? Something is irreducible. I got this silly clicker on this, too easy to push things. So P is irreducible if and only if, whenever, right? So whenever P equals AB, so it's different, right? So if P equals AB, it's certainly the case that P divides AB, right? But it's also true that A and B divide P, right? So that should sort of seem strange, but that's not strange for units, right? For example, right? So whenever P equals AB, then P is an associate of A, or P is an associate of B, right? So what does this P is an associate of A mean? It means P equals UA for some unit U, right? So this is exactly equivalent to saying either A or B is a unit, right? I mean, it really means the same thing, right? So there's really kind of two ways of writing this part here, right? By the way, this is an equivalence relation, right? If P is an associate of A, then A is an associate of P, right? Because if P equals UA, then clearly A equals U inverse of P, right? Because U is a unit, so we have inverses, right? So it's symmetric, right? It doesn't matter which order I do it in, right? If A is an associate of B is an associate of C, right? Then that means that A equals UB and B equals UC, or some U prime C, right? Some other U, right? And so what does that mean? Well, A equals U prime C, right? But this is a unit too, right? What's the inverse of U prime? Let me just keep doing some extra algebra here. So U and U prime are both units in this little picture, right? So what is the inverse of U? I'm claiming that U times U prime is also invertible. What is its inverse?
U prime inverse U prime U prime inverse.
Yep,
U
good.
inverse.
Yes, good. All right. So you
Okay.
get a point. You finally get a point. So you remember to turn the order around, right?
Yeah.
So if you like remembering silly things, it's like the shoes and socks theorem thing, right? Okay. Now, is it always true in an integral domain that prime, and I know we did this last week, that prime implies irreducible?
Yes, but we couldn't go the other way around, right? We couldn't go backwards.
Yeah, so this direction was always true, right?
Yeah.
This direction's always true. And you can't go the other way around. And we gave a nice example, right? And so it's worth just sort of remembering this nice example because it's also examples. Whoops, it's not that. It's this. Right, so if we take Z and we adjoin -5, right? So this is just a set of things like A plus B square root of -5, right? Where A and B are real. Not real, in Z, right? Like that. Let's see, does the same thing work in R? I haven't really thought about that. Maybe the same sort of thing works in R. But anyway, we'll do it over Z here, okay? This had an example of something which was irreducible and not prime, right? So that's the example this thing had. And so the example was, I gotta remember, 2 plus square root of -5, 2 minus square root of -5, right? So we multiply those two things together. This is the conjugate, right? So this is like ZZ bar, right? So when you multiply two things like that together, it's just this squared plus that squared, right? And y plus squared because there's an I in there, right? So so this is 4 plus 5, which is 9. right? Remember doing this last week? I remember it like it was yesterday at this point. 3 divides this, right? That thing there. 3 certainly divides 9, right? Okay, but 3, whoops. But that means that 3 divides this to minus square root of minus 5, right? So it divides that, right? But 3 doesn't divide either of those things, right? And we proved this last week too. 3 does not divide 2 plus square root of minus 5, and 3 does not divide 2 minus square root of minus 5, right? Not divide, right? So this says that 3 is not prime in this ring, right? 3 is not prime in that ring. Okay. We also did an argument to show 3 was irreducible, right? I actually showed that all of these were irreducible. We showed that 3, 2 plus square root of minus 5, and 2 minus square root of minus 5, all of these things are irreducible. Right? What tool did I use to prove that? You remember? Again, I'm doing an example that is in your text, by the way. I mean, I'm not going too far out of the text to grab these examples here. I mean, they may have used square root of minus 3 or something, but it's the same basic example.
Is it an acronym?
No, we used a particular kind of mapping going from this space into into Z. Yeah, I guess into Z anyway. No, actually into Z plus, into Z. Yeah, and to N, right? I guess is what we actually did, right? And we called this an arithmetic norm, right? And it had the property that N times AB equals NA NB, right? And that's really all we used about this norm in order to show this irreducibility, right? Why would that be important in irreducibility proof? We take one of these things over here, just call this thing over here, I don't know, S, right? Any one of these things, and suppose S equals AB, right? Then what I would get here is I would get NS is equal to NA times NB because of this multiplicative property, right? But then we showed this, that can't be the case, right? That can't happen in this case. Or I mean, what we really showed is that one of these would have to, one of the NA or NB would have to be 1, right? And if NA or NB was 1, then A or B would have to be a unit, right? So again, this multiplicative property actually tells me that if I have this give me the value 1, then this is a unit, right? So so I guess that's particular to the definition here. So this particular definition was NA is equal to A bar, right? It's just A times its conjugate, right? And that's exactly the same, right, as the length of A, the magnitude of A squared, right? Right, in this structure, right, in that structure there. I mean, these are complex numbers, so magnitude's the usual magnitude, right? The length of the complex number, right? Am I saying something? I'm seeing some frowns actually. So am I saying something that is not understood here? Like, you know, if Z is A plus BI, right? Z bar is A minus BI, right? Z bar is when we multiply this stuff together, right, is A squared plus B squared, right? The cross terms go away because of the minus sign, and we get B squared I squared, right? But you know, so we would usually get, I mean, what do you get when you multiply these things? You get A squared minus BI squared, right? But BI squared is actually plus, right? I mean, so, I mean, just let me, here, I'll work out the algebra, right? We actually would get here A squared minus BI squared, right? Why is that? Well, we know that, right? Because X plus Y, this is just a algebraic fact, assuming you have distributivity and stuff, right? this is going to give me x squared minus y squared, right? So that's definitely true. So that's true. But I squared is minus 1. So this gives me a squared plus b squared, right? Okay. How did we get this? I mean, this is just complex numbers. How do we get that thing? Well, you know, again, NAB is equal to AB bar, right? By definition, right? But if I conjugate a product, A times B, conjugate its product, that's A bar times B bar. This is AB, A bar, B bar, right? We're doing products in complex. We have commutativity, right? So this is A bar, B bar, right? And so that's in A and B, right? So the productive part is easy to show there, right? Anyway, look at the notes, review that, right? Because this is a really nice example of all sorts of things. It's a nice example of where irreducible and prime are different, right? Okay. It's also true, is it true that this ring, z square root of minus 5, sits inside of this ring, z square root of minus 1? I guess that's not quite true. Yeah, I guess that's not true. That's not quite what I want to say. Is it true that this ring, z square root of minus 5, I'll go bigger than that, sits inside of C, right? Is everything in here a complex number?
Yes, because it's
Yeah.
it's I.
Yeah. So we'll see. Let's see. In fact, do we even have? Yeah, I guess trivially, C is a unique factorization domain, right? Because there are no units, right? Everything is a product of units. So there is no way to contradict. This is what we might call vacuously true, right? There are nothing to be irreducible in C. So it's a unique factorization domain, right? We just saw that in here we have irreducible and prime are different, right? And part of the lecture for today is that if we're in a unique factorization domain, prime and irreducible have to be the same, right? So here we have a subset of a unique factorization domain, a subring of a unique factorization domain, which is not a unique factorization domain, right? So that's sort of a really nice true-false-like question, right? Is every subring of a unique factorization domain a unique factorization domain, right? So you would say false, and then you need to give me an example, because that's what you have to do. And you say, oh, here's a good example, right? Okay, so it's a good example to keep in mind. I mean, you know, these are sort of good things to keep in mind. That's the reason also, I mean, this same example is in the book for the very same reason, right? Okay. Okay, so let's move on. So what did it mean to say that something is a unique factorization domain, right? It meant there's sort of this existence and uniqueness part of the argument, right? And so it was that everything, you know, in R, so I have some integral domain. We're only talking about integral domains throughout this day, right? And so everything in R can be written as a product of irreducibles, and that product of irreducibles is unique, right? So A can be written as B1 through BK, where BI are irreducible, right? So that's part of it. This is like the existence part, right? And then we need also this uniqueness part. And so that's going to say if A is written as some other product of irreducibles, like Q1 through QL, right? Then what do we need to know about these? We need to know that L equals K. In other words, you have to have the same length, right? So that's one thing. And we need to know that there's some permutation. So now this is actually just Q1 through QK because we have the same length, right? So we need to know there's some permutation of K, right? Such that PI is nothing but an associate. We can't say it's actually the same as, but is an associate of Q sigma I, right? So in other words, I can reorder these Qs, kind of line them up with the P's and such that everything's an associate of each other, right? so that everything's just a unit off, right? It's just like throwing in a bunch of plus and minus ones when you're in Z, right? Okay. So that's what it means to be a unique factorization domain, right? So, you know, keep that definition in mind, right? It's defined in terms of irreducibles, right? Not primes. It's defined in terms of irreducibles, right? So this is an important fact. Good. Good. All right. So see, I don't actually. I'll just keep going through these. I mean, we're pretty close to the end here, so we'll get through this and look at those examples. I know I did this last time. So what was a GCD domain? When do we know? So we're in a ring R, right? And I'd like to take an A and B and R. I mean, this is good just for thinking, right? What would it mean for D to equal the GCD of A and B? You know, like, what does that mean? Because we don't have any notion of less than or equal, right? So there's no ordering, right? So greatest here needs to mean something slightly different, right?
So let's say you have, it would mean that D divides A
So
and
D divides
divides
A
B,
and B, right? D divides A and D divides B.
and
So that's one condition, and the other is going to be. So that's like, is a divisor of.
yeah.
Right? Now, how
And
do we say is the greatest divisor of?
If there was some other thing, then like, I don't know, C, I guess. Like if there was some other variable in the mix, it would divide D, meaning that.
So another variable that divides both A and B. So some C such that C divides A and C divides B. Then what's the relationship between C and D, right? That's what you're getting at.
Then C would also divide D because D is the greatest.
Right? C would have to divide D. Good, right? So yeah, that's what it means to be a greatest common divisor. Now, is the greatest common divisor unique? Well, it's unique up to units, right? We could always multiply by a unit, right? And we could even do that in Z, right? We could multiply by plus or minus 1. We'd still get it, you know, sort whatever we meant by greatest common divisor. This definition doesn't distinguish between plus and negative, right? Okay. Good. All right. So if we're in a GCD domain is a domain, an integral domain, so that every A and B has a greatest common divisor, right? So that's a GCD domain, right? Okay, and then we had this argument that said that if we're in a GCD domain, if R is a GCD domain, then in particular, irreducible implies prime. Okay, so we get that. All right. And that means both ways, right? Because prime implied irreducible anyway, right? So we got that. And now that this direction did require that we're in an integral domain. If you look back at the proof, we did use the fact that we get a product. One of the two product the product that's 0, right? So one of the two pieces had to be 0. That's exactly what we used, right, to get that. Okay. Now this proof I know I went through last time, so I'll just sort of point to it here. I think it's worth just thinking about. You might just try to do it, right? So there's this kind of weird intermediate thing where I define something to be primal. And the primal, so R is primal. It's kind of a mixture of these two things, right? So if R divides AB, then we don't just say R divides A or R divides B, right? We say then R equals ST, right? Where S divides A and T divides B, right? So it's a little kind of a mix of the two things, right? So it's like, this is kind of like being prime. I mean, being prime would be R divides AB implies R divides A or R divides B, right? This is saying R divides AB means I can split up R into something, right? Such that one or the other part divides A or B, right? So it's not quite prime, right? It's a little bit different, right? If R was irreducible and primal, right, then the only way we could split this up is for one of those to be a unit, right? So if we're irreducible, then in fact, one of these has to be a unit. So the other one has to basically just be R. It's got to be an associate of R, right? But that would mean that R itself divides A or B, right? Because if an associate of R divides A or B, then R divides A or B, because we're only off by a unit, right? We can always multiply by U inverse somewhere, right? Okay, so clearly if R is irreducible and primal, right, then we have that we're prime, right? Okay, so the key thing is that in a GCD domain, okay, I'll make that a C. In a GCD domain, all elements are primal. So that's the trick, right? So for every element R, right, that divides anything, right? So notice that rules out zero by having this hypothesis, right? Zero can't be one of these things. For every element R, or it's like zero is trivially primal because this doesn't happen, right? Then R equals ST, where S divides A and T divides B, right? So you can do that. Okay. And then, so I'm not going to redo the proof because I think it's worth, you can just try to do it or you can just look at it. But basically you just use the fact that we have a GCD to build S and T here, right? Okay, so I mean, you could try to do this proof without coming up with the notion of primal, but it's really easy just to get yourself confused, right? And once you have this notion there, this proof is so easy, it seems like the right thing to do. Right, so it's kind of a nice example. But anyway, if we're in a GCD domain, then we're primal. I think that's where I actually stopped last time. So I think up to here, this has all been review, so to speak, right? So the next claim was that if I'm in a PID, then we are a GCD domain, right? So that was kind of the next real claim, right? And so this is a nice little proof here. So PID implies GCDs exist, right? And now the trick is to again think back to Z as our inspiration, right? When Z was our inspiration, we saw that the GCD of A and B, so this is in Z, right, is equal exactly to the ideal A plus B, right? And this is that old, Bezo's theorem, right? Because this is saying that XA plus YB is equal to D, let's call this D, right? Is equal to D for some X and Y, right? So that's sort of where that's coming from, right? Okay, so we want to use this in the PI. We want to use this idea, right? So this is an interesting thing, right? We're using an intuition from Z, right, to come up with this proof here, right? It's almost like magic, except we already have this intuition, right? So that's the nice thing here, right? So now I'm just in a PID, right? That's all I'm assuming. I'm in a PID, right? I take two elements, A and B, and I build this ideal, right? So now remember in this ideal, this is literally just this is literally the set of all, R plus S, where R is in A and S is in B, right? So, I mean, we did this kind of thing way back when we were talking about building new things from old things, right? Which is actually part of these same notes, right? It's still in the same notes. Okay, but since this is since this is a PID, this I that we built here, right? It is generated by a single thing, D, right? Okay, so let's show that D, we don't know what it is, right? In Z, we have a way of building this thing. We can find the GCD, right? We use Euclid's method and find the GCD, right? In an arbitrary integral domain, we don't have that, right? If we're a PID, we know this thing exists, but that doesn't mean we have any way of getting our hands on it. We just know it exists, right? Okay. Z is special because we have the division algorithm, right? What about, just out of curiosity, what about fx? Can we always find this, like the thing that's giving us our ideal, like the thing that witnesses being a PID? I mean, how did we originally show that this was a PID? We actually had this intermediate step where he said any Euclidean domain is a PID, right? So Euclidean domains are contained in PIDs, right? And we showed this is Euclidean, so we need some sort of Euclidean function, right? So that, we take something in here, P of X, and some other Q of X, and we can write down, or let's say, Q of X, we can write this down as SX QX plus RX, right? So there's something like a remainder, right? And the Euclidean function was something that defines, it would send this to some integer, some n, say, it would send this to some m, and this m had to be less than n, right? It had to be decreasing, right, like that. So when we're looking at polynomials over a field, right, the Euclidean function we're using there is the degree, right? So given an ideal in fx, right, if I want to find something that generates that ideal, I just take any polynomial of minimal degree, and I'm done, right? And if you want to make it unique, you can take the unique monic polynomial of minimal degree, right? And that'll give you the ideal, right? And of course, I can multiply that monic polynomial by any element of f because those are all units, right? It doesn't change anything, right? Okay, so anyway, let's go back to our proof, right? So that I'm just reminding you how we got those things there. Right, so we're in a PID, so I take my A, I take my B, I generate the ideal from A and B. Since I'm in a PID, there is a D, right, that gives me this ideal, right? Okay, so in particular, this means that A and B, I mean, first of all, both the ideals A and B are certainly subsets of A plus B, right? That's certainly true because this ideal has 0 in it, right? So anything in here plus 0 gives me something in there. Right, this ideal has 0 in it, right? So anything from here plus 0 gives me something from here, right? So this containment is clear, right? But this is D, right? And what's the relationship when A is a subset of D? What is the corresponding division relationship? What's the division relationship between A and D if A is a subset of D?
A can divide D.
Or it's one other option. Can you think of any element in A, the ideal generated by A?
You said what is an element that can generate A?
Just give me some element in the ideal generated by A.
0.
Okay, that's one obvious choice. Is there another obvious choice? The ideal generated by A. Can you think of something in the ideal generated by A? I mean, 0 is true, right? But it's not quite useful.
A?
A is in the ideal generated by A, right?
Mm-hmm.
Okay, so in particular, if A is a subset of D, then A is an element of the ideal generated by D, right? When is something in the ideal generated by D? What does it mean to be in the ideal generated by D?
It's an A plus B?
I mean, we're just looking at A and D here. B's not in the picture right now. I mean, right now I'm just saying, what does it mean to be, so what is the ideal generated by D? What objects are in here?
The
A
whole
and B.
Forget A and B. Now I'm just asking a question about D, right?
the whole set of A.
Like I
Seriously,
said, forget about, look, what's in the ideal generated by X? Forget A and D and B. What's in the ideal generated by X?
X.
X is definitely in there. So so just to be a little bit, we're in an integral domain. So in particular, we're commutative plus unit, right? Unitary.
So X for sure.
X squared.
X squared's in there. Yeah.
Okay.
0.
Zero's in there. We already got that one.
X
Okay.
plus 1. X minus
Well,
1.
X plus 1 and X minus 1 are definitely not in there,
Oh.
right? Because if X plus 1 was in there, then X plus 1 minus X would be in there. And so
Oh,
1
okay.
would be in there. And if 1 is in there, it's got to be all the whole ring, right?
Mm-hmm,
So we've got 0, we've got X squared. I'm an ideal. This is an ideal. So what is that? What are the properties of being an ideal? How are you an ideal? What does this subset of R have to satisfy to be an ideal?
Is something with an inverse? Inverse or identity? Okay.
Someone say something correct. If you want to check something's a normal subgroup, the first thing you have to do is know what normal subgroup is, right? And then you have to check it. If you want to check something is an ideal, the first thing you have to do is know what an ideal is and check it, right? What do you need to have happen to be an ideal?
So the axioms are like additive subgroup, right? You have to have addition.
Yep, that's one of it. So it's got to be an additive subgroup. Good.
And it has to have multiplication.
But by what? So this is the important part here.
Is it by a ring element?
Yeah, from a ring.
By an arbitrary ring element, right?
Yeah.
So if I'm an ideal, it's got to be the case that Ri is contained in I, right? And IR is contained in I. Now here we're commutative, so it doesn't matter which order I do this in, right? So in the commutative case with unity, when I'm generating from a fixed element, right? This is just the set Rx. It's just the set of all Rx for R and R, right? Like over Z, what are the ideals? Like 2Z is an ideal. 3Z is an ideal, right? Over f of x, what's an ideal? Like f of x times, the field f of x, right? That's an ideal, right? So in order to do your problems this week, you have to know that representation for ideals, right? So now back up to here. Okay, so now we've figured out what the ideal is. Okay, what does it mean for A to be in D? What is D? D is anything times D, right? So what does it mean for A to be in RD? I'll just keep spilling out. This is a set of all RD, such that R is an element of R. Whoops, R. Right? So what does it mean for A to be in this?
A divides that.
What does it mean for an element to be in this set? Here's a set of shapes. Is it true that this is in that set? Okay, is it true that this is in that set? Why? Because it's one of those shapes, right? What does it mean for something to be in the set? It needs to be one of those things, right? So what does it mean for A to be in this set?
A has to be one of those things.
Good. So what does that mean?
Is that where you, it's like is it called associative? Or
No, I'm just asking you, what does it mean to be one of these things? A has to equal what?
RD?
RD. So does D divide A?
Yes.
Yes, because A is equal to RD, so D divides A, right? Okay, so now working backwards, A element of D means D divides A, right? And that was coming from that, right? So again, I mean, I've said this many times, and this is something you really, 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 really need to get down. A contained in D means exactly the same as D divides A, right? The order gets flipped, right? This is kind of like a less than or equal here. This is like a less than or equal there, but they're kind of flipped, right? In the fancy language of math, we would say this is a co-category, or this is like a co-functor or something like that. It swaps the order, right, of things. Okay, going back up to our proof that was supposed to be really clear. So I've defined A plus B, where in A, now I've forgotten what we're doing actually. This is kind of so far. Oh yeah, I'm showing that the PID is a GCD domain, right? So we've taken this ideal I, right? We're in a PID, so this ideal I is just D, right? We know that, right? The ideal generated by A and the ideal generated by B are contained in there. So in particular, they're contained in D because these are all equal to each other, right? But since A is contained in the ideal generated by D, that means D divides A, right? And since B is contained in the ideal generated by D, that means D divides B, right? Okay, so A plus B equals D implies D divides A and D divides B. That's part of what we needed for having a greatest common divisor, right? Okay, what was the next part we needed? We needed to know that if C divides A and D, so if C divides A and C divides B, then C divides D, right? Okay, so turn this into a statement about containment of ideals. So what does D divides A mean in terms of ideals?
A and C.
Say it again.
Let me
What's
make
the
sure I have
rela-
it backwards.
What's the relationship between A and C?
The
and
A
A
is
and B.
contained in C.
Yep, you flip it around, right? A is contained in C, and right like that, right? Okay. Sorry, B. Sorry, this is C. These are both C, right? So A is so if this happens, right? This tells me that, and that tells me that, right? Okay, but if A and B are contained in C, that means that the ideal A plus B is contained in C. Because this is the smallest ideal that contains A and B, right? It's the ideal generated by those two ideals, right? But this ideal is D, dang it, D, right? So this tells me that D is contained in the ideal C.
So they're the
So
same.
no, they're not the same.
Oh,
What does this tell me about divisibility?
that C can be divided by D.
No, remember you flip the order.
Oh, that D can what?
You flip the order, right? Just like you did up here, right? C divides A means A is contained in C.
Oh, gotcha.
D
So C is
contained in C
dependent
means
D.
C divides D, right? That's what we needed for our conclusion, right?
Yeah.
Right. So we start off with this hypothesis, turn it into a statement about ideals, right? Extract this statement about ideals and then turn it back into that and get the conclusion, right? So in a PID, this is the GCDs, right? So in other words, writing this out, in any PID, this is true. Right, in any PID. So in particular, this is true, for example, in FX. right? For f of field, right? Because you know, because of the Euclidean division algorithm, that fx is a PID, right? Right. That's one of the first things we proved when we started looking at PIDs, right? It's a Euclidean domain, so it's a PID, right? So you know, this tells me things like if f of x and g of x are relatively prime, right? So what does that mean? Well, it means that the ideal generated by f of x plus the ideal generated by g of x is the entire field fx, right? Because that's what relatively prime meant for ideals. If I add the two ideals together, I get all of R, right? Then that tells me, let's see, do I even need to say that? Oh no, I didn't want to even, what do I want to say? I'm not even sure what I want to say. I guess I didn't really even want to say that. Forget the relative primeness. I guess I just want to say that these are, you know, these are given. There is a greatest common divisor of those two polynomials. I guess that's all I want to say, right? Because we know this is generated by a single polynomial, right? So, I mean, it's not actually completely trivial. You know, maybe try to show it yourself, right? I mean, try to show that given two polynomials, right, over any field, that there's a greatest common divisor of those two polynomials, right? Without using the theory that we're doing. I mean, using the theory we're doing, it's clear, right? You know, now this isn't giving me a nice method of doing it. I'm saying, generate the ideal of all these things. Let's say kx. I mean, here's the method we have right now. Generate the ideal of all polynomials like that. Huge infinite set of polynomials, right? Of these, take the one with least degree, right? That's going to be this greatest common divisor, right? So this is not an efficient way to find d of x, right? Okay. Now, if you go back and look at what we did with the Euclidean algorithm in the number theory section, the first chapter 0 of the class, right? I gave you a way of coming up with so there we had that if a and b were relatively prime, there's some x and y such that a plus b, not relatively prime. If the GCD of a and b is d, we could find some x and y that gave me this combination, right? This is the thing I'm looking for, right? And there was a method for doing that, right? And that algorithm works exactly the same as polynomials as it did over Z, because it just uses the Euclidean algorithm, right, for division. So the very same method works. I think you might even have some homework that asks you to find some GCD. I don't remember now or not, but there might be a problem that asks you to find some GCDs or something. Okay, so anyway, a PID is definitely a GCD domain, so PIDs. So in PIDs, irreducible and primes are the same. Yay, right? So that's good. Okay. All right. The main thing we want to get to is PID implies UFD, right? That's sort of the place we're really kind of trying to head here. Okay. So one important thing is that F, let's say R PID does not imply RX PID. All right, and we would really like things where if R is, something, then Rx is also something, whatever property that is, right? So that turns out to be true for UFDs, but not for PIDs. So we need one more property here. So R is Noetherian. By the way, when you're trying to prove unique factorability in the integers, right? What is it you need to do? I mean, where do you need to actually do? You take some, so show in Z that any n factors, uniquely up to permutation as a product of primes. All right, so how did that proof go? You said, well, I mean, there's kind of two ways of doing it. You could say, suppose that, let's do it by contradiction, right? So suppose that isn't the case, right? Then you say, well, if it's not the case, then let n be the least. Let n be the least non-factorable. Actually, let me not do it this way. Let me do it the other way, because it's going to mirror what I'm going to do next, right? So let me just take an n. So take n and z, any old n and z. Okay. Suppose n can't be factored as a product. So just the existence part, actually. Suppose n can't be factored as a product of primes. Okay. So n is in z, not a product of primes. I mean, nothing about the axioms of number theory say that there have to be primes around at all, right? They fall out of the theory. Okay, so what can I say about n? Can n be prime? If n is prime, is n a product of primes? Yeah, right. So n is not prime. So if n is not prime, then it is composite, or like we like to say now, is reducible, right? So n equals some other things, a times b, right? Can both of these be factored as products of primes? Because if this was a product of primes and that was a product of primes, then when I multiply those two products together, I definitely have that n as a product of primes, right? Now, one or the other might be a product of primes, but at least one of them is not a product of primes, right? So I can go down and get like an n1, right? So what I have here is I have n, and I have n1, which divides n, right? But in particular, n is bigger than n1 because when we go down in divisibility, we go down in size as well, right? This cannot be factored as a product of primes, so I can then go on and find an n2, right? The same argument just keeps working, right? So I can find an n2 that divides n1. Yeah, whoops, here I want to say less than, right, etc. Now, why can't I get this infinite descending chain in divisibility? Well, can I have an infinite descending chain in positive numbers, positive integers? No, and that's because induction, right? I mean, the least member principle, right? You can't have an infinite descending chain of positive numbers, right? So we know this has to stop, and so once it stops, we have a contradiction, right? Because there was nothing stopping my proof. I can just keep doing it over and over and over, right? So it must be the case that n initially was writable as a product of powers, a product of primes, right? Okay, so we're going to do exactly the same proof we need something to replace our use of induction, right? That's the point. We need something to sort of make a kind of finiteness here, right? And so the something is this. So R is Noetherian if and only if there's no infinite increasing sequence of ideals. So I'll also write this out in math. So there's nothing like this, none of these. If I0 is a proper ideal and I1 is a proper ideal and I2, etc. forever, right? That can't happen. Now, what does that have to do with divisibility? Remember, when we change from divisibility to ideals, right? This divisibility here would say n is a proper ideal and n1 is a proper ideal and n2, right? Like that, right? So this infinite chain of divisibility corresponds to an increasing chain in ideals, right? Are there infinite decreasing chains of ideals in Z? So can I find an infinite set of numbers, say N1, that divides in 2, that divides in 3, going up like that, right? That would correspond to N1 contains into, now I got to be careful, contains into properly, contains, so infinite decreasing sequence like that.
We're
Right.
descending this time?
I'm just saying, I mean, we kind of argued that we can't have an increasing infinite sequence in Z because that would corresponding to a descending sequence of numbers, right? Okay, so now my question is just think about it for a second. Can we have an infinite increasing, sorry, an infinite decreasing sequence in Z of ideals? So can we, so notice that here, this is dividing that. These numbers are actually getting bigger, right? So definitely the least member principle isn't going to come in and say there's a problem, right? Can I do something like 2 and then strictly bigger than 2 times 3 is strictly bigger than, 2 times 3 times 5, right? Etc. Right? So I can keep going forever there, right? No problem. Okay. In fact, you don't even have to do this. I could even do 2 is strictly bigger than 2 squared, is strictly bigger than 2 cubed, right? Etc. Right? So there's lots of infinite decreasing sequences of ideals in Z, right? Nothing stopping that from happening. Okay. Okay. So, but there can't be infinite increasing sequences because that would corresponding to decreasing natural numbers, right? So in particular, Z is a Noetherian domain, right? It's Noetherian. It's a Noetherian ring, right? So Noetherian just means there's no infinite increasing sequence of ideals. Okay. So what we want to show is we want to show that, let's see, I guess I can say, I don't think I need the GCD domain. Let's just see what I can do. So I want to claim if R, oops, is an integral domain, and R is Noetherian, then every element of R can be written as a product of irreducibles. And I want to just do exactly the same argument I just did. Okay. And we're definitely using, so I'm actually not here assuming that we're in a situation where primes and irreducibles are the same, right? So I'm not assuming that here. We're definitely using irreducible for this part of the proof, right? So here I'm going to do exactly the same argument, right? So let R be an element of R. Suppose, towards a contradiction, if you like, that R is not a product of irreducibles. Okay. So can R be irreducible? If R is irreducible, is it a product of irreducibles? Yes, right? So the first thing to know is that R is not irreducible. Right? But that means that R can be written as some S times T right? Can it be the case that both S and T are products of irreducibles? So if this was a product of irreducibles and that is a product of irreducibles, is R a product of irreducibles? I'm just multiplying together two products, right? So there's definitely no problem there, right? So what does that mean? One of these two things has to not be a product of irreducibles, right? So let's take this one. Let's call S. Let's say R1 is not a product of irreducibles. But now I'm back in the place I started, right? I mean, R1 has the same property that R did, right? So I can just keep going, right? So what we get here is we get R, let's go backwards here. So start off with R, let's call it R naught, so I just have a starting place. And I get R1, which divides R, right? It is also not a product of irreducibles. I get R2, which divides R1. It's not a product of irreducibles, right? You just keep going like that, right? Now, when we turn this around, right, what we're getting here is we're getting R is contained properly in R1, is contained properly in R2, etc., right? Very same argument as we did with Z, right? There's no difference in this argument. This can't happen, right, because we're in a Noetherian domain, right? Okay. So for the existence part of this argument, we just need to be Noetherian. Okay, so just like with the integers, there's an existence part and a uniqueness part, right? So the existence part doesn't require prime and irreducible being the same. Okay. Now, what about the uniqueness part? Now here I am going to be just a little bit sloppy. This is really an induction, and you'll see exactly what I'm saying. This is exactly what you would do if you were teaching this to kids almost, right? So suppose I have something where I can take an element of R. So I already know I can write it down as a product of irreducibles, right? So I take A and I write it as a product of irreducibles. But now I also write it as a product of irreducibles again. Right? So maybe K and L aren't the same. Maybe these are just completely different irreducibles, right? Okay. But then what can I do with this? Right? Well, now I'm going to use the fact that irreducible equals prime. Okay. So now I need to add an extra thing here. I need something to make sure irreducible is prime. So let me put in that I'm a GCD domain. So Noetherian and GCD domain now, right? Now I've got these, let's see, and in fact, in this argument, I guess I'm not using the Noetherian, I'm just using the GCD. Now, I don't know, maybe in some weird way, I mean, I'm using the fact that I have this representation, right? So I guess I'm saying, if I'm in a GCD domain, if I'm in a case where irreducible and prime are the same, and I have two different products of irreducibles giving me the same element, I want to say these two products have to be the same, up to ordering and units, right? The usual thing. So how do you do this? Now here's where I'm going to be sloppy, right? I just take P1. P1 definitely divides P1 times up to PK, right? Because P1 is a factor, right? Everyone okay with that? Right? Okay, so that means that P1 actually divides Q1 up through QL. Right? But P1 is prime. Right? So P1 is prime. So that means that P1 actually divides some QI like that. Right? But QI was irreducible. Right? So that actually means that QI and P1 have to be associates. Right? So that tells me that P1 is an associate of this QI. Right? So I could reorder them so that QI was actually Q1, right? I'm just going to change the order. Right? And then I could divide both sides by P1, right? And so then I would get that 2, okay, I would get a unit, right, times up to pk is equal to some unit, right, times q2 up to ql. Right, so I can put as many units here as I want to, that doesn't matter. The point is I got rid of one thing from both lists, right? So here's where I'm using induction sort of in a silly sense. One of these lists is going to run out, right? I mean, let's say k is, just say k is less than or equal to L, right? So at some point I'm going to get up here and I'm going to take out all of these. So I'll end up with 1 on this side and I'll have a unit. And if I have anything left over here, I may have like qk plus 1 through ql, right? But that can't happen because then these irreducibles would have to multiply by this unit to give me 1. So in particular, qk plus 1 would be a unit. All of these would have to be units if this happened, right? Because, just because this thing times that thing, whatever this product here was, would be a unit, right? Because it's multiplying to give me 1, right? That can't happen because these were reducibles, right? So that tells me that this can't happen, right? So k equals L, right? But once I've sort of worked through everything, then I've paired these things up so that everything's an associate with the other thing, right? So how would you do this formally with induction? You would say something like, suppose there's a counterexample. Let me take a counterexample with least length, right? And then you reduce it to a shorter counterexample, and that'd be a contradiction, right? Something like that, right? So you would do induction. You're still using induction somewhere here, but you're doing induction now on an index, right? That's just an integer, right? That's not some weird element of a ring, right? Just the number of terms in the sequence, right? Okay, so there is a hidden induction here. So the upshot of all this was, altogether, is that Noetherian plus GCD domain implies UFD, right? And the other thing we showed above is that being a PID implies Noetherian and implies GCD, right? So PID implies UFD, right? Okay, so that's the main thing here, okay? There's an argument here that, there's an argument here that's wrong. So in the video, I made this argument more correct, right? It still gets a little bit messy at the end. So I need to rewrite this argument. This is true. If R is a UFD, then Rx is a UFD. That's true, okay? But it's a little bit tricky because what you really do is you say R is a UFD. You go to the field of quotients over R. It's a nice proof, actually. You go to the field of quotients over R, and you sort of compare Rx with FRX. Okay, and you show that something in here can factor into irreducibles exactly when it factors into irreducibles over here. All right, and that's actually a theorem in your text. It occurs twice in your text. It occurs in chapter 17. Let me pull up your text real quick. Let's see, I forget where the other place it occurs is. Let me, how to get the... Yeah, it's right here, Gauss's lemma, and then 17.2. Reducibility in Q, which is the field of quotients over Z, right, is equivalent to reducibility over Z, right? So this is something that you've probably used already in some exercises. It's something that you definitely will need to use like in your exam. I mean, because I know last time I did the exam, I had a couple like this. The same proof shows what I'm trying to show here, is that irreducibility over R for RA UFD is equivalent to irreducibility or reducibility over over F of R, the field of quotients, right? So it's the same argument and lifted up to that case. as long as the original polynomial is coming from Rx, right? It's interesting to, I mean, here, yeah, anyway, I'll just leave it at that. I forget where else this comes up. It comes up. I forget where else it comes up here. I can't remember where it was. Somewhere they have this theorem in your book anyway. It's in there somewhere. I just can't remember where it is. But they don't prove it. They just say go and look at that proof and it's the same, more or less. Right? That's what they do. I've lost track of my thing. That's it. Okay, that's it for these notes, right? So that's all the theory of ideals. I mean, this is something we started like 3 weeks ago, right? So I mean, all this stuff. So I mean, this is definitely incorporated in your chapters wherever we started this whole thing. 16 through 19, or no, even before that, 15 through 19, wherever this started. And then there's all this sort of nice stuff. So once we have all this theory out of the way, right, we can start messing with polynomials, right? So that's kind of the nice, it's kind of fun part of this stuff, right? So I'm through with this set of notes, right? And so now what we can do is look at some of the homework problems. We had talked about looking at 25 and 36, maybe. Is there anything else you would like to look at? Let's see, this is your last week again. So I guess I need to promise getting you an exam. I'm going to say by sometime on Thursday because I have so much to do. Like I've lost these first 2 days and I have so much that has to be done tomorrow that I'm not going to promise by tomorrow night. I just can't. So I'm going to promise you by sometime on Thursday.
So we don't have class next Monday then?
We'll have class, but it'll be to ask questions just like last time, right? Just like always. We always have in these two classes, at least when I teach, the reason I made these week 4 and week 8 like this is really just for catch up and for asking questions about the exam.
Okay.
Now, if you have someone else teaching a class, I don't think any of the other classes you take will have that structure. It's only right now actually 571 should have that structure, but it depends on who's teaching it, right? So if I taught it, I would do the same sort of thing, but whoever else is teaching it might do something different. So we will have a meeting, but the meeting will basically be for you to ask questions and go over things that might come up, right?
And I assume exam number 2, we're not gonna be able to like self-grade and stuff like that?
No, you will. So you'll turn it in on Wednesday. I'll have to set a hard deadline, right? So you'll turn it in on next Wednesday. Well, not not tomorrow, but the next Wednesday. And I'll give you until like the weekend and I'll post the solutions right after you turn it in, right? And then you will have until like the end of the weekend, say, to do corrections, right?
Okay. Yeah, even though we'll be starting a new class, we'll still have access to like Halo and stuff like that?
You'll keep access to this class for a couple of weeks, yeah.
Okay, cool.
and I can post grades. I mean, they may gripe at me, but I can post grades a little bit late. Yeah. Good. All right. So yeah, let's look at a couple of these homework problems because they're fun too. So what sort of really fun stuff did I not talk about here? I just want to point out there's a lot of. I think this is a really fun chapter. It's too bad we can talk about this next week if you want. But there's some really sort of cool uses of this abstract derivative, right? Just using the properties of a derivative in algebra, right, to sort of define something that's abstractly a derivative. I mean, there's no limits here. You're not working over reals or anything like that, right? You're just applying the rules of differentiation to polynomials, right? And then proving theorems with these things. So it's kind of fun that works. And that's kind of an interesting thing. And they give you a lot of like criterion for multiple zeros and stuff. Anyway, there's a lot of kind of fun stuff in this chapter 19. And if you get bored, there's a lot of really fun stuff in 2021 Galois theory. I'm not sure where they get to Galois theory here. So I'm not sure that they actually get to Galois theory in this book, which is sort of a shame. Way at the beginning, I posted this set of videos from the visual group theory guy. He does a nice quick pass at field theory and Galois theory. If you're interested in just getting a quick look at it, I mean, because that's really kind of where all of this is headed in a sense. So it's kind of nice to take a look at it. And so I was just watching those videos. I mean, it's like what he calls lecture 6, and there's, I don't know, maybe 4 or 5 videos in that set. And he doesn't go through all the details, but he does a nice job of sort of indicating what's going on there. All right. Anyway, I mean, if you're interested, I would suggest that. But for now, let's just look at some homework. Guess I have to get it up. Homework 6. Oh, you know what? Actually, let me just open it like this. Let's just do it like this. Do I keep this stuff? Do I keep it here? I've got so many glasses, I can't remember where I keep things. I think it's here. Oh, I didn't mean to edit. I just meant to look at it. Let's see. I think we were talking about chapter 19. Yeah, so 16 is really kind of interesting. It falls into this category, and then we said 25 and 36. Let me go. 25 is this one, and 36. Let me see what 36 was. Oh yeah, 36 is this one. Yeah, okay, yeah. So let's look at these a little bit anyway. And let's see, is the whole problem? I think the whole problem is here. So here it's asking about the order of the splitting field of this polynomial over Z2, right? Okay, so this is fun. So order is, I'm not sure why they call it order here, but it's the size, right? The size of the splitting field is what they're saying. So let me get this so I can see both at once, maybe. Let's see, shrink that, sorry. Okay, so x to the 5 plus x to the 4 plus 1, right? And they're kind enough to factor it for you. I think this was already done. I don't think you had to do this. Am I right? This was already given, right, in the problem. Okay, now you can check, you can multiply this together and see that, and this is over Z2 of x, right? So you can multiply this together and just verify that this is what you get, right? That's a good thing to do, right? I'm not going to do that right now. What I want to do is actually consider the splitting field question. And let's see, it doesn't matter which one of these two you start with. I think I started with this one. Okay. So if I'm going to try to add a root here, what's the first thing I need to check? Let me just call this one here f of x and call this g of x for a second.
The discriminant
What is the discriminant? Why do I want to do that?
tells you how many roots there are.
I mean, we're in Z2X, so there's no square roots. I mean, I don't know, maybe there's square roots. I shouldn't be too, I mean, it is useful to think that way, right? But I don't want to go down that path, right? I want to use what we're currently learning. And what we're currently learning makes this much easier than that. So how do I, given a polynomial of degree 2 or 3, what's an easy way to check that it's irreducible over Z2? You do have to read your text too, right? I mean, everything I've done in class is covered in the text in a slightly different form, but there is stuff in the text that I haven't covered in class, right? Like all this stuff about polynomials. So if I have, so first of all, if I'm in a field, right, and I have, so here's sort of a basic fact, right? If I have an f, so forget these up here. If I'm in a field, right, in f of x, and this thing has a linear factor in f of x, right? So this thing could factor into something, you know, cx plus b times some other gx. Whoops. Right? So if that were to happen, right, then what could I say? Could I pull out the c here and say this would be?
Could we do this like the mod method? Like figure out what is 1 mod 2?
I mean, that'll come, right? I'm looking for something slightly different here, right? So, I mean, this is sort of standard stuff, right? So I'm saying I have a linear factor, right? I'm in a field, so I can pull out the c, right? So I get this, right? But then this b over c is an element of my field. In fact, minus b over c is maybe what I say, is an element of f, right? Because it's a field, right? But this is a root, right? Of, in other words, f of this minus b over c is 0, right? So if I can pull out a linear factor, I have a root, right? If I have a root, can I pull out a linear factor? I think so, right? Because I can divide, right? Because we have the division algorithm, right? So if I have a polynomial, I'm in a field, right? Now it's important that we're a field here, right? In fx, right? And I have that f of a is 0, right? Then I can divide x minus a into whatever, right? In fact, when I'm dividing by a monic polynomial, I don't even need to be in a field. I can do this, right? I think we talked about this a little bit before, because I need to cancel out these things along the way. But since this is monic, I can always do that, right? So we can always, you know, get some q of x up here and get some final r of x, which is the remainder. And what property does the remainder have? It's got to have degree less than that, which is degree 1, right? So this is degree 0. What does that mean this is actually? It's just a number, right?
It's just a constant.
Just a constant, right? And so what we would get when we did this division is I would get f of x is x minus a times g of x. I mean, I don't know if you've taught algebra 2 even or something, right? You teach stuff like this, right? Because you use synthetic division to evaluate functions and stuff, right? So that if I divide this by f of a, what I get here is that f of a has to equal r, right? Because this gives me a 0 when I plug in a, right? So if I have a root in the field, right, I definitely get a linear factor, right? So I have a linear factor even if and only if I have a root, right? A linear factor. I mean, this is important. I don't know that my polynomial factors, because it might not have a linear factor, right? But if it has a linear factor, it has a root, right? But when I'm looking at a polynomial of degree 2 or 3, right? If it factors, it's got to have a linear factor, right? This is one of the things used over and over all over the place in your book. This is one of the things you should have seen, right? If I need to check that a polynomial has a factor and it's degree 2 or 3, I can just check the elements of f, right? And see if they give me roots, right? Does that make sense, right? If I've got something, if I got a polynomial of degree 2 or 3 and it factors, in other words, it's not irreducible, right? Suppose it's not irreducible, right? And it factors, right? One of these has to have degree 1, right? So this has degree 2 or 3. Right? So one of these will have to have degree 1, right? But that means that means there is a linear factor. That means there's a root, right? You know, so this it'll mean that f has a root. Whoop. So if f is of degree 2 or 3, it's irreducible if and only if it has no root in f, right? So you can just check to see if you have a root. Right? Now, in R, that would be hard. You've got infinitely many things to check. In Z2, it's not, right? You have 2 things to check, right? So you look at your little polynomial here, right? That one right there. If I plug in 1, do I get 0 mod 2? Oh, no, I get 1 plus 1 plus 1, which is 3, so that's 1 mod 2, right? If I plug in 0, I get 0 plus 1, which is 1 mod 2, right? So no root there, right? So this polynomial is irreducible, right? This polynomial here, very same reasoning, is irreducible, right? So these are both irreducible polynomials over Z2, right? So now that we know they're irreducible, right? Now I can make this, I can take my first one, which I called, actually, how do I do this? I tried to do this yesterday. I couldn't get it to do it. So I want to copy it. And I would like to paste it here. How do I do this? Oh, there we go. Oh, no, I just want it there so I can still see it. Right, so there's my fx, right? So now I can do this. Okay. So you're supposed to now understand the structure of this thing here, right? So first of all, this is irreducible, right? This is where we're using the things we just learned. It's irreducible. Is it prime? Yes, because f of x is a PID, it's an integral domain, whatever you want. I mean, it's a PID or it's a UFD. So it's prime, right? It's a PID, so is this ideal, is it maximal? Is every prime ideal in a PID maximal? Yes, that's another thing we had last week, I think, right? So it's maximal. So this thing here is a ring divided by a maximal field. This is a field, right? Because when I take a ring and I quotient out a maximal ideal, I get a field, right? So this thing here is some new field, right? It's an extension field. It's a field that contains f of x and it extends it, right? These are the extension fields, right? This extension field has a root of f of x. What is the root of f of x? I'm going to let alpha be some particular element in here. What are the elements in here, right? So a thing in here, right? If I take something in there, it looks like this. It looks like h of x plus f of x. The ideal, right? That's what an element in there looks like, right? Okay. Which h of x's do I need to look at? Because we have the Euclidean algorithm. I'm dividing by something that's a quadratic. So what degree would the remainders have? So I see some mouths moving, but no sound is coming out. If I divide some polynomial by a quadratic polynomial, what degree can the remainder have? Or I guess there's a couple of options. What's the largest degree a remainder can have?
1?
1, right?
Yeah.
So these things here, the representations here are really of the form ax plus b plus my ideal, right? That's the only things that are here, right? That's all that's there in this structure, right? Of these things, which thing is a root? Can you think of something that will definitely be a root here?
Mm,
This is like, hold on. Let me get your text here. Go. Let's see, is this chapter 19? Yeah. Let's go to the very first. Let's see. I need to make this a little bit smaller. Ah, here we go, right? So it's 19.1. Ah, the very first thing in chapter 19, right? What is the thing that we use for a root? We use x plus f of x, right? What happens when I evaluate f on x plus f of x? I will get f of x plus the ideal. I mean, this is an ideal, right? So in other words, I'm applying a polynomial f to x plus I, right? I mean, the polynomial is just a polynomial, right? It's kind of this formal thing, right? So, you know, it could be like whatever polynomial it is. But I'm applying a polynomial to x plus I, right? What happens? Well, the way ring operations are defined here, right? If I do, you know, if I add two things, I just add them here, right? If I multiply two things, I just multiply them here, right? So, you know, I just get f of x. I mean, let me not use the same f. Let me use a different f. Okay, sorry, to make this more clear, right? So I'm looking at things. I'm looking at some h of x, some polynomial in fx, right? And now I'm going to come along and compute h of x plus I, where I is that ideal, all right? And you just think about the way this is defined. Well, I'm going to get just exactly h of x plus I. That's what I'm going to get. Right? Because x squared becomes, you know, x squared plus I. You know, ax becomes ax plus I, right? So the polynomial just becomes h of x plus I just becomes hx plus I, right? Okay. And so in particular, if I take fx, so now this is generated by fx, so f of x plus I is just fx plus I, right? But that's just, you know, fx plus fx. Well, clearly that's just fx, right? That's just zero, right? In this ideal, that's just zero, right? So the root you add sort of formally is x plus fx. That's the thing you add for your root, right? Yeah, let's see. Okay, we can do this too. What do we want to say here? Yeah, I think this is right. Okay, let me see if I think I have this right. So if I take an arbitrary, sorry, now I'm going to think for just a second. I didn't think, I'm not sure why I haven't thought this through before. So if I take cn x to the n plus c naught plus fx, right? This is like cn alpha to the n, because this x to the n will just become alpha to the n plus fx, right? Because I can pull these, you know, okay, so yeah, what am I doing here? So I can, you know, we've got this, whoops. That kind of construction is going on in fx, right? But I can move this fx back through all this stuff. So this is like, you know, cn plus I times, you know, x plus I to the n, etc., right? You can sort of do that to it, right? Because that's the way these operations are defined, right? So this whole construction here can just turn into cn alpha n plus dot 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 plus c1 alpha plus c naught, right? So what does this look like? Remember when we talked about polynomials over fields when we were doing linear algebra? Right? This looks like a vector space with n plus 1 coefficients, right? Remember this p, remember p n of x, or I don't know, maybe you call it r. I forget how we denoted it then, right? But this is like the set of all polynomials, you know, where degree p of x is equal to n, right? And this was a n plus 1 dimensional vector space, right? With basis, you know, 1x, x squared through xn, right? All that stuff. Everyone in linear algebra, shake your head, because we definitely did plenty of this. Yeah, okay. Right, so the point is we can take an arbitrary thing from our E, which is always given by, in this case, it's always just given by something like this, because this was a second degree thing, right? Right, and we can always just sort of write that as some C 1 alpha plus C naught, right, for this one root. Right, because I'm just sort of taking the fact that our alpha that we're looking at is that. We can take an arbitrary thing in there and sort of do this thing to it, right? And so in this case, we don't need to go all the way up to some n. We can just go up to 1 because all the remainders just have degree 1, right? So instead of thinking of this fx over fx as being, you know, this sort of construction of hx plus fx, right, etc., right? You can think of it as just, I mean, just like we do like q square root of 2, right? What is that? That's the set of all a plus b square root of 2. Right? Very common, and that's a field, right? You know, you can divide, you can multiply, you can do 1 over a plus b squared root of 2 by using the conjugate, stuff like that, right? So this is a field. This is exactly the field qx modded out by x squared minus 2. All right, so what are we doing? We're just taking a root, right? Now in this case, we're taking a root from somewhere where we knew what roots are, right? So here we're doing the same thing. We're saying instead of thinking of this field like that, right, add this one root alpha, right? And we're really just now thinking of the field f alpha, right? Now what was this alpha? Well, formally it's this thing, right? So formally it's that thing and it's living in there, right? But we can just think of it as f alpha, which would be the set of all a plus b alpha, where a and b are in f. Right? And so in a very natural sense, this f alpha has degree 2, right? It's got 2 parameters, you know, over f, right? It's a 2-dimensional vector space over f, right? But it's also a field, right? And we can do the same sort of thing. I can multiply by the conjugate, you know, and do the same sort of thing here, right? So if my initial polynomial was 3rd degree, then I would have a dimension 3 vector space over this, right? If my initial irreducible polynomial was degree n, I would have a dimension n minus 1, right? Space over this, right? Sorry, n dimension n, right? I got to add 1 back to it, right? So same dimension as the degree of the polynomial we're modding out by. Okay. So this you all got to think about carefully, right? Think about exactly what's going on here. We're adding a root. So here we added a root to q. We added square root of 2. Right? What does that actually mean, right? Formally, we might say, well, what it really means is we're doing this, and we're just calling square root of 2 equal to x plus x squared minus 2. Formally, that's kind of what we're doing here, right? We're adding something that whose square is going to be 2, right? That's kind of what we're doing. Okay, so in this case, right, we're starting with z2 x. We're modding out by x squared plus x plus 1. That's the thing we're modding out by, I think. I've lost track of the This is 25, and I can't find it. Yeah, that's right. It's that, right? And so we've added this root alpha, which is really just x plus x squared plus x plus 1, right? And we're looking at, so this is, and now we're looking at Z2 adjoint alpha, right? And so what this, we can just represent this as A plus B alpha, right? For A and B in Z2. Right, so we can think of it like that, where this is a root, right? Okay, does that make sense? We're doing the same thing, but it's often much easier to think about those things there. Okay, and what property does this alpha satisfy? Well, it satisfies the property that alpha squared plus alpha plus 1 equals 0, right? That's the property that it satisfies, right? Okay, when we add a single root to a field, and when we're modding out by a degree 2 irreducible polynomial, we added one root. Is this already a splitting field for that thing? Is the other root necessarily already in there? So in other words, so in this thing here, right, there is a root. So, I mean, let's just go back to this question. I'm in a field. I've got a degree 2 polynomial. Let's say just p of x of degree 2. Suppose I have a root in here, right? P of a equals 0. I have a root, right? So I know I can go through and divide, and I get here, the p of x is equal to some constant times x minus a times some q of x, right? What degree does this have to be? It's degree 2, right? So this has to be degree what? This is degree 1, this is degree something, and the 2 degrees need to add up to 2. So what is the degree of this?
Also 1.
Also 1, right? So this is linear, right? So in fact, I can pull out another constant if I need to and get some d x minus a, x minus b, right? I can factor it over f, right? So if I have a polynomial of degree 2 that has a single root over a field, right, then both roots are there, right? Because I can just do that. I can just do, it's basically the division algorithm, right? So here I've taken a field, I've added a root. I did not have a root over Z2, but I've added a root here. Does this polynomial completely factor in Z2 alpha? Well, yes, because it has a root, and that's a second degree polynomial, right? So it completely factors here, right? So Z2 of alpha is a splitting field. It factors completely there for this thing, for x squared plus x plus 1, right? What is the other root? Like once I give you a root of a polynomial, again, this is something we teach kids, right? When I give you a root of a polynomial, how do I find, let's say I give you a quadratic and I give you one root, how can you find another root? And that's kind of, without using anything but division.
Just divide the polynomial.
Yep, you divide, right? So I have a root, namely this x minus alpha. Right now, where am I working? I'm working in this field E, right, which is the same as this f alpha. Right, so now I'm going to do this, right? So I'm going to multiply here by x, right? That gives me x squared minus alpha x, right? And so down here I get, so I subtract, right? And I get alpha plus 1 x. All right, so what do I need to do here? I need to multiply by alpha plus 1. All right, and so then I get, when I do that, I get alpha plus 1 x. And then minus alpha times alpha plus 1. Right? And then I have this 1 up here. So I bring this down and I have alpha times alpha plus 1, right? Bringing that down. But what is this in this thing? Well, this, if I expand it, is alpha squared plus alpha plus 1. That's 0, right? So the remainder is 0. Right? So the two roots for that polynomial is x minus alpha, where that alpha is just the one I added there, and the other one is x minus, well, it's split like this, right? So x plus alpha plus 1. Right? That's what it splits into, right? Because we just divided it with remainder 0, right? Right? So that was kind of fun. I mean, it's different, right? You're getting these different roots like this, okay? Now the next question is, we've got this other one, x cubed plus x plus 1. Now you see, Jessica, why I was surprised to see how little you wrote, right? Because there's all this stuff going on, right? Okay, now the question is, because we're trying to find the splitting field over f, right? And we've taken and we've added f alpha, and now we've got to sort of consider this polynomial over the field f alpha. Right? So now we have to say, is this irreducible over that? Right? So that's the question. And if it is, then we're going to do the same thing. We're going to add a new beta, right? So that, and then we start the whole game again, right? So how do we do that? Well, what are the, and again, here we can just say, what are the elements here, right? So like, what's a complete list of all the elements here? So we have 0 and 1, that's from Z2, right? We have, how do I want to continue? So I have, by the way, how many, so we know this is so we knew that f alpha over f was two-dimensional, right? So everything is of the form a plus b alpha, right? Where there are 2 options there and 2 options there, right? So it's 2 times 2. So there's 4 options that we have, right? So what I have 0 plus alpha, I have 1 plus alpha, I've got 0 and 1, that's it, right? That's all that's in there. Right, in this very small field, right? That's all that's in there. Right, so the whole field is just 0, 1, alpha, and 1 plus alpha. That's all there is. I guess we could have found our other root by doing that instead, right? Because that's the only other thing there is there. Right, so that would have been another option. The division works in an arbitrary field, but this would have worked there too, right? Okay, so is this irreducible over that? So clearly 0 and 1 don't make this 0. Does alpha make this 0? Is it true that alpha cubed plus alpha plus 1 is equal to 0 in this field? I mean, what we know is that alpha squared plus alpha plus 1 is equal to 0. We could do the same kind of thing we did before and divide, right? If I want to ask this question, I could say, I could just do this, right? You know, and do I get a remainder 0, right? That's what I could do there. Can I do something else? I mean, here I can say that alpha cubed is equal to what, minus alpha minus 1, and so that's also alpha squared. I mean, if this were true, right? If this were true, if this, then I'd have that. So then I'd have alpha squared equals alpha cubed, right? So then I would have here alpha times alpha what, minus alpha times alpha squared minus alpha. Oh no, I can, yeah, sorry, I get alpha squared times alpha minus 1 equals 0, right? But I'm in f alpha, which is a field. So what would this mean? If alpha squared, so this is we're in f alpha here. I mean, you can argue You can argue just like you would anywhere else, right? Alpha squared and alpha minus 1 is 0. We're in a field, so we're definitely in an integral domain, right? So if this was 0, I'd have to either have that alpha squared equals 0 or alpha equals 1. Does either one of those two things happen? If alpha squared is 0, then alpha would have to be 0. Is alpha 0 or 1? Are you shaking your head yes, Emmy?
No, I'm looking here at the alpha minus 1, and I thought we were plugging in 1 minus 1 to be 0.
No, we're in the next field up now, right? So we've moved on to F alpha.
Yeah.
And we're dealing with this x cubed plus x plus 1, right? And we're asking, is this thing irreducible over F alpha? Not over Z2 anymore, but over F alpha, right? Now, F alpha has 4 things in it, 0, 1, alpha, and 1 plus alpha, right? So we know 0 and 1 are not roots of this. We checked that before, right? So now I'm asking, is alpha a root of this? I'm doing the same kind of check I did before. I'm just saying, is alpha a root, right? So what I did up here is I said, if alpha is a root, I mean, this is what I argued up here, then alpha equals 0 or alpha equals 1. Well, is it true that alpha equals 0 or alpha equals 1? Whoops, or alpha equals 1.
Is that not what we said right now? That alpha is 0 or alpha is 1?
No, I said, if this is true, right,
Yeah.
then alpha equals 0 or alpha is 1.
Gotcha.
So, but is alpha 0 or 1? Alpha was the new thing we added, right? It's not 0 or 1, right? It's the new root, right? So there, this is false. So this doesn't happen, right? So alpha is not a root of that. Is alpha plus 1 a root of that? So is alpha plus 1 a root of x cubed plus x plus 1, right? So now we just asked the same question. So now I've got alpha plus 1 cubed plus alpha plus 1 plus 1. Is this equal to 0, right? So that's our question now. Or again, I could divide, right? I could just do long division. You could, in fact, let's do it that way since before I did this other thing. So let's do long division instead, right? I could do x cubed plus, I mean, because this is how you would normally check a root, right? Is it true that I could do this? Would I get remainder 0, right? So let's check. Let's say x squared, did I get x cubed minus alpha plus 1 x squared, right? So we come down, I get alpha plus 1 x squared plus x, right? So I multiply by alpha plus 1. And so now I get alpha plus 1. Oh, no, alpha plus 1x, right?
Yeah.
Alpha plus 1x squared. And I get minus alpha plus 1 squared x, right? And then I subtract again. So I have alpha plus 1 squared x plus x. Sorry. Is that what I want to say? Yeah, I guess.
It's a negative.
What am I doing? Now I'm getting myself confused.
Plus 1 squared plus x. Oh no.
Oh yeah, so I'm just getting a plus 1 here. So I'm getting, yeah. So that's right. So I'm getting alpha plus 1 squared plus 1 x, right? And now I bring down this 1, right? And so here I need to add, right? Alpha plus 1 squared plus 1, so that cancels out. And then here I have minus, and we have alpha plus 1 times, and I've got to multiply by all this stuff, alpha plus 1 squared plus 1, right? That's what I have there. And so when I subtract, I get alpha plus 1, and then alpha plus 1 squared plus 1 plus 1, right? And so if it divides, this should be 0. Right? So now the question is sort of, is that 0? I think that is actually equivalent to having just plugged in alpha plus 1 squared in there, right? And checking to see if it's 0. I think we've got exactly the same thing, right? I mean, once I move this in, we have exactly the same thing, right? Because this is alpha plus 1 cubed plus alpha plus 1 plus 1, right? And this is just exactly x cubed plus x plus 1, substituting alpha. So we didn't save any time or effort there, right? Okay, so what is this thing squared? It's alpha cubed. It's alpha cubed plus 3 alpha squared plus 3 alpha plus 1. I mean, you can do all this normal expansion, right? There's nothing strange about that. Then I have here a plus alpha plus 1 and a plus 1, right? And of course, now these are all, these coefficients are all in Z2, right? We want to keep that in mind. So we got alpha cubed. This is now plus alpha squared. This is alpha, right? Then I have a plus alpha plus 1 plus 1 plus 1, right? So the 2 alpha, that's going to go away because we're in Z2. 2 of those will go away. So now I'm at alpha cubed plus alpha squared plus 1, right? And, oh yeah, and so now what do I know? I know that alpha squared is equal to minus alpha, or sorry, what we started with is alpha squared plus alpha plus 1 equals 0, right? That's how we added alpha, right? It was a root to that, right? So alpha squared is equal to minus alpha minus 1, right? So this is alpha cubed minus alpha minus 1 plus 1, so that'll go away, right? And so this is alpha cubed minus alpha, so that's alpha and alpha squared minus 1. And I can do it again. Yeah, I guess I'll do it again. So this is alpha, this is minus alpha minus 1 minus 1, right? So again, now that's minus 2, but that's actually 0 again, right? So now I'm getting minus alpha squared down here, right? So minus alpha squared is alpha plus 1, right? And that is not 0, right? So the remainder, I mean, the remainder has to be something. Where's our field again? I mean, let's just sort of rewrite this. We're working in F alpha, right? This all together, alpha 0, 1, alpha and 1 plus alpha. We already saw that, right? We saw that those are the two roots of x squared plus x plus 1, right? And we're checking roots for everything. Whatever the remainder is, it's got to be in the field, right? So it's got to be 0, 1, alpha, or alpha plus 1, right? And we just did all that work and got that it was alpha plus 1, right? But alpha plus 1 is not 0, right? Okay, so there are no roots to x cubed plus x plus 1 in this field, right? So what do we need to do? We need to add a new root. What root do we add? We add beta equals x plus x cubed plus x plus 1. That's a new root, right? And so now we're going to look at the field F alpha. Whoops. Dang it. Okay, stop. Beta, right? We're adding that root, right? So what is this? Well, this is the set of all, A plus B beta, right? Where A and B, oh, sorry, no, in fact, this is a cubic, right? So now this is a little bit worse, right? So this is A plus, let's say A1 plus A2 beta plus A3 beta squared, right? Where A1, A2, and A3 are from F alpha, right? Like that. And so this is a 3-dimensional vector space, right? So F alpha beta is a 3-dimensional vector space over F alpha, right? And that is a 2-dimensional vector space over F, right? So altogether, we are a 6-dimensional vector space over F, right? So, I mean, maybe you kind of see the way this goes, right? So now we've added this beta. Are we done, right? Is this a splitting field now, or is there more stuff, right? So that's what you have to think about, right? So what would you do here? Maybe you take this and try to divide. You take x cubed plus x plus 1 and try to divide by x minus beta, right? And see what you get. All right, you get some quadratic, right? So we're way over, so I guess I'm gonna have to quit at this point. But you see there's a good deal of stuff to do here. I mean, this is all written up in the solutions, right? So, I mean, you should take a look at that. But this is the kind of thing you need to do for here, right? You're trying to do this field extension. You've got to add a root, check to see if you've got all your roots, right? In the first case, you had all your roots. Check to see if the next polynomial is still irreducible over that extended thing. In this case, it is, right? And so now you have a possibility of 3 roots. Are they all already in there, or do you need to extend some more to find those roots, right? So when we divide this thing, we get some quadratic. Is this quadratic reducible or irreducible over f alpha beta, right? That's sort of the question you're at, right? So a lot of computational stuff working in funny fields, right? It's kind of, I don't know, it's kind of fun, I think, right? Anyway, I'm gonna have to stop there. It is all written. I mean, the solutions are all there in the notes. So part of the question was, is 25 different from 36? Abby had asked that. I think the answer is yes. I think in this case, you have to do a whole lot more work because you keep not getting everything in the first field. I believe in 36, it turns out just to be a splitting field already by itself. I'm pretty sure that's the way it works out. Right. So anyway, I think it's kind of fun stuff, right? It's fun stuff, and it uses all the sort of theory that we've used. I mean, we're really having to use the theory that we use to get PIDs, you know, every prime ideal is maximal, irreducible is prime, all that stuff, right? You're having to use just to do these funny little calculations, right? Anyway, I will see you next week. I will post the exam. If you see anything that you think is wrong in the exam, let me know immediately so I can fix it, right? And wherever I post it, I will also post the usual sort of correct. If I need to make corrections, I'll post them there too. So keep an eye on that, right? So I'm not going to take, if you get to the end and say, oh, I made this, I had the original version and I didn't see you made these changes, that's not going to fly, right? You already know ahead of time that changes can sometimes need to be made. So you should keep an eye on that. Okay. Good. All right. So I will see you next week, same time. Do you want me to post the video, or do you not care for this? So you got to turn on. I can't hear you.
I would like you to post it. Yeah, because I
Okay.
watch it back later.
Okay. I'll do that. You can practice having AI like summarize it for you, or turn it into a podcast or something. Okay. All right. I'll see you. Bye-bye.